Find the displacement at C and the slope at A. Assume that EI is constant. So as I look at here, C is going to be right here in the middle. A is going to be the one-hand side. We can do this problem, writing out the full equation of the elastic curve using the calculus method. This gets a little bit more, not tricky, more cumbersome just because we have this distributed load, then we have a concentrated load. As complex situations go about, this one wouldn't actually be too terrible to write using the calculus method. But since all we really care about is the maximum displacement and the slope, it's just a lot easier to go about using our method of superposition and putting things together. And so the first thing we have to do is we have to take a look at this and then compare it to our tables to figure out how we're going to put it together. Now, there's a couple different ways you can look at this. You can sit there and go, well, I could find whatever a situation where we have the entire beam is loaded with a distributed load, and then figure out and subtract part of the distributed load. And actually, the way that you'd subtract part of the distributed load is you'd kind of assume that it's coming from below. You can then add the concentrated load. Fortunately, if we go and look in our engineering equation manual for the simply supported beam, and it's very important to make sure that you're looking at the simply supported beam and not the cantilever beam, because since the equations start off, because these are all based off the equation of the elastic curve, since they're all coming from what the boundary conditions are, you're going to get much different answers if you're plugging in simply supported like this situation as opposed to a cantilever beam. So I look at this, I can go, well, I've got a distributed load on the first part of it, concentrated on the middle. And so what we do is, this is what we're going to end up doing. So we're going to calculate out what the slope and deflection are based on this one right here, which is the half distributed load. I'm going to add to that a point load right in the middle. When I overlay those two together, and I'm just going to find the equation and add the two of them together, that's going to give me my situation that we have right here. So let's begin. Let's do the displacement first. So we're going to look at that vertical displacement at C, and we're just going to completely do that. And what I have here, this is a copy of the page in your engineering equation manual. I'm not going to give you the page number because depending on what version you are, it's going to float a little bit. And so what we're going to do is I want to identify what I have. Well, the first one here is my load placed right in the middle. And then I also have right here, I have my load that is a distributed load halfway across. So easy enough. And so now we want to start with the deflection. And so the deflection at the midpoint here. And just notice, what it's given you here is the maximum deflection. But they also tell you where the maximum deflection is going to be in this picture, which is right in the middle, which should make sense. Now, if I look down here, it gives me the deflection. Now, the distributed load on the first half, you'll notice that the maximum deflection is listed not at half. It's actually at 0.4598 times L. But they do list you right here what the vertical displacement is going to be at x equals L over 2, so right in the middle. Because typically they know that that's what you're looking for, is what's going on in the middle. So how do we handle that? So we just write down, I get the Vmax from the first situation, so negative PL cubed over 48 EI. And it's listed as negative because, as we talked about shear moment diagrams, going for vertical displacement, which is listed as V, your textbook may list it as Y. I don't remember off the top of my head. As we're looking at displacement, going up is positive, going down is negative, just like with our regular Cartesian coordinate system. And then what I'm going to do, I'm going to add to that this guy here. So it is negative 5WL to the fourth over 768 EI. So this is 1, this is 2. Okay, and so now we can sit there and plug things in, because we do have our loads, and we actually have all of this information. So for the first one, the load is going to be 8 kilonewtons. L. Now L is the overall length of the entire thing, so that's 8 meters. Divide that by 48 times EI. And looking at that, we forgot, or at least I forgot, this is, that's not supposed to happen. Let's go back. This is L cubed, not just L. And if we would have looked at the units, that would have been apparent to us. So anyway, so for picture 1, that concentrated load, if we go and we multiply all these numbers that we have together, what we're going to end up with is negative 85.33 divided by EI, and those units will be, see, that's a kilonewton meter cubed over EI, so that'll be kilonewton meter cubed. So for us to add these two together, we're going to have the same unit, so hopefully that will all work out. Well, let's look at part 2. And so we have all this information too, so negative 5 times W. W is the intensity of our distributed load, which is 2 kilonewtons for every meter. And then we have our length, so 8 meters to the fourth, divided by 768 times EI. And so looking at the units here, because we do have meters to the fourth here, we are going to end up with kilonewtons times meter cubed. Now, obviously, that's not all of it, because you have the EI, but we're just going to solve this in terms of EI right now. And then if I plug the rest of this into my calculator, what I will get is negative 53.33 over EI. Okay, so how do I find the vertical displacement at C? Is I just take those two, add them together. So situation 1 is negative 85.33 over EI, kilonewtons per meter cubed, minus 53.33 divided by EI, kilonewtons meter cubed. So the vertical deflection at C, due to condition 1 overlaid with condition 2, is going to be negative 139 over EI, kilonewtons per meter cubed. That's it. We're just looking up, basically matching one picture, matching the other picture. And so that takes care of our vertical displacement. Now let's go and do the same thing with the slope. So now we need to do the slope at A. And so once again, let's just highlight. This is situation 1. This is situation 2. And so now we need the slope. And we need the slope all the way at the right-hand side. So if I look down here, slope 1 is listed. It's that guy right there. Now, it doesn't list a slope 1 or 2 on here, but it does list slope max, which will be at 1. So it'll be that guy there. So we have all of the equations that we need. So if we look at, let's switch that away from the highlighter. So if we look at situation 1, which is our concentrated load, it's negative PL squared over 16 EI. So negative 8 meters, sorry, not meters, it's 8 kilonewtons. The length's in meters, 8 meters squared divided by 16 EI. And so what we'll have is, we'll call that theta 1. So theta 1 for condition 1, if we go and we multiply that together, that's going to be 8 times 8 divided by 16, so 32 over EI kilonewtons meters squared. And so now if I look at my second one, we have negative 3WL cubed over 128. Oh, forgot the negative sign then. And what's the negative sign mean? It just means because positive is counterclockwise, negative is clockwise, so it's just a rotation in the clockwise direction. So W negative 3 cubed over 128 EI. So negative 3 times 2 kilonewton per meter times 8 meters cubed over 128 EI. As we can see here, we're going to end up with the same units of kilonewtons times meters squared, which means that we will be able to add everything together, which is good, because that's what we want. We want to be able to add everything together. And now, if I just multiply all those units out, negative 24 divided by EI kilonewton per meter squared. And so that tells me that the angle at 1, the slope at 1 is negative 32 EI kilonewton per meter squared minus 24 divided by EI kilonewton per meter squared. So when I superimpose those two together, my total slope will end up being negative 56 kilonewton per meter squared divided by EI. So remember, EI is just kind of like the stiffness matrix of the beam, modulus elasticity times moment of inertia. But there we go. So we were able to take that more complex loading and break it down into the two parts and just superimpose them on top of each other to find out what my maximum deflection and my maximum slope are.